Hi everyone, Krishna this side. So in this video, I'll be covering this LeetCode problem 3620 network recovery pathways. This problem is from biweekly contest 161 and it's good problem to consider. So yes, decided to make this video. You can pause the screen and read the problem statement, okay? And these are the examples that I'm given. This is the first example. In inputs, we have given an edge array online and there is this k value has been given to us. We'll see what this basically means and what we have to do with them. This is the second example, okay? And these are the constraints that are being given to us. All right, so now let us directly focus on the screen. Let me just connect it first. It is not connected. Yeah, so what we are given is we have given a directed acyclic graph having nodes 0 to n minus 1. So in total we have n nodes, okay, and those nodes starts from 0 to n minus 1. So here 0 1 2 all these nodes are there. So last node is basically 8. So in total n value is basically 9. 9 nodes we have, and those nodes starts from 0 to n minus 1, and this graph is basically acyclic and directed. We see that these nodes are all directed edges, okay, these edges basically, okay. Now next is we have given online array. This basically states that whether a particular node is online or offline. If its value is false, like for board its value is false, okay, so this node is actually offline, it is not online. That is something what it basically says. All the other values are true, only this 4 is offline, okay. So that is something what it basically says, and we will see what it is basically trying to say. And k value is also given. So these three values basically given. The first is like edges. So this edge basically represents there is a edge between 0 to 1, okay. This particular first array that we see, there is an edge between 0 to 1 and its weight is basically 5. So when we see here in explanation as well, there is this edge between 0 to 1, okay, which is having weight as 5. There is edge between 1 to 3, okay, 1 to 3, and its weight is basically 10. So that is something what it basically says, this edge array, okay. So with this, what we have to do is we have to start traversing from this particular node 0. Okay, we have to start traversing from 0th node and we have to reach to the last node. So here last node is basically 8. Okay, we have to start from the 0th node, we have to reach to the end node. So we will get multiple different ways, right, to reach that one. So from here to here, there is one particular path. Okay, then there is this path. Okay, this is the second path that we have. Okay, next one is like this is the third path. Another one is like following this one, there is a path, this is last path, okay. There are different ways to reach to this last node that is there, okay, starting from the 0th one. So these paths are only considered valid path only if any intermediate node that we have, okay, all these intermediate node that we get it following this particular path from 0 to 8. So all this intermediate path should be online, okay, all these paths should be online. If at any point in time, if any node is offline, this basically shows this online offline, okay. If it is offline, definitely that path is not a valid one. So from this particular one, this particular path is not a valid one because this 4 is actually offline. This basically says right here f is been given, so it is offline. So this path is not a valid one. So we are not considering this particular path. Next is total edge cost should be less than or equals to k. Okay, total edge cost. So these costs are basically given to us, all these costs. So when I start traversing from this particular path, the total cost that I get is like 10 plus 8 plus 10. In total, it is 28. Okay, and it says that this total cost should be less than or equals to this k value. At any point in time, if this cost is basically exceeding this k value, that path is not a valid path. So from here to here, when we go, it is like total 28 is something what we are getting it, and k value is 26. So 28 is actually greater than this 26, which is not following this particular condition. So it is an invalid path. So this path is an invalid path. If I try to consider this particular path, total cost is like 10 plus 6 plus here is 6 again. So in total, it is like 22, which is actually 22 is actually less than this k value. Okay, so this is a valid path. Okay, this is valid path. And the second condition is like we have to just check that all these intermediate nodes that we are getting it, those should be online, and these nodes are online. Okay, so this path is valid path. Okay, so yes, we got to know that like from starting from 0 to last node, when we start traversing, we just have to take care of two conditions. All the intermediate nodes should be online, and the total cost that we are getting it from 0 to last node by following that particular path, it should be actually less than or equals to this k value. Okay, now we get different paths, right? Like this is a path which is a valid one. This path is also valid one. When we add all these values, it gives us valid path. This path is also valid one. This particular path and this last path that we are having, it is invalid. Only these two paths are invalid. Rest are valid one. Now what we have to achieve? Okay, we are getting three different paths which are valid one. So among these three different paths, okay, this is the first path which is having total cost as 22. So when we start considering this particular path, which is the minimum value that we are getting it, the cost of this edge is actually minimum, right? The minimum edge cost that we are getting, that is what we have to consider. So when I start considering this particular path, here it is 10, 6, 6. Out of all these 10, 6, 6, minimum value that we are getting is 6. Okay, either this or this. Okay, 6 is the minimum answer that we are getting it from this particular path. Okay, let us say that, okay, 6 is the answer that I am getting it by considering this particular path. Next one is like, this is also valid path, this particular path. When we add them, 5 plus 3 is 8 plus 6 is 14. 14 is the valid path. So this particular path is also a valid path. Okay, because its k value is basically it is less than this k value, and uh, this online status, all these nodes, intermediate nodes are online. Okay, so yes, this is a valid path. And from this particular path, what is the minimum value that I got? 5, 3 and 6. Out of these, 3 is the minimum value that I am getting it. Okay, by following this particular path, 3 is the answer that I am getting it. Next path is like last, this particular path is a valid path. When we try to add them, 4 plus 3 7 plus 6 is actually 13, 13 6, 16 plus 6 is 22. 22 is actually less than this k value, sorry, less than this k value. Okay, so yes, this is a valid path, and all these nodes are also online. So yes, we can consider this as a valid path. So by following this particular path, which is the minimum value that I got, 4, when we compare with 3 6 3 6, 3 is the minimum that we are getting it by following this particular path. So yes, from this particular path, 3 is the answer that we are getting it. Now, out of all these minimum values that we got, which is the maximum one? That is something what we have to print into the output. 6 is the maximum answer that we are getting it. Okay, that path was this particular path. So yes, 6 is the answer that we have to print into the output. Okay, so now the idea is pretty much clear. Out of all the minimum cost that we are getting it by following this part, maximum answer is something what we have to print. Okay, so relation is something what we have to consider. Out of minimum, all the minimum, maximum something what we have to consider. Okay, or there is another statement like, out of all the maximum, minimum is something what we have to consider. Okay, whenever we see these kind of statements in any questions, we simply try to think whether we can apply binary search or not in this type of questions. Okay, that is something what we have to think about it. Okay, whether we can apply binary search or not. Okay, if it is possible to apply binary search, we will simply solve this type of questions with the help of binary search. Okay, so yes, that is the whole idea. Now the question is pretty much clear, like what we have to achieve from this one. And whenever this type of statements comes, it is not guaranteed that if this statement basically says minimum out of maximum or maximum out of minimum, it is not guaranteed that this question will be solvable with the help of binary search. But we have to think about this type of questions in that particular direction, if it is possible or not. If it is not possible, whatever the brute force approach that we can apply, we have to apply it on those type of questions. Okay, so let us suppose that if someone doesn't get this idea, like minimum out of maximum, we have to apply binary search and how we have to apply. The simple approach that comes in our mind is like, let us start exploring all the different nodes. Like from zero, we have these three different paths. So we will simply use either BFS or DFS. Whenever we start traversing for any graph related questions, we have two techniques, right? Either the first is like BFS, second is like DFS. So in BFS, we will use Q. In the DFS, the stack is something what basically get used whenever we keep on calling the functions recursively. Internal stack is basically works in that particular case, but for BFS approach we will use Q. So here we can solve this one with the help of Q as well, but that is a brute force approach. Like we will start keep on exploring, sorry, we'll keep on exploring all the paths. Like from here, there is one path, from here another path, and while traversing we will keep on calculating their total sum. What is the total sum so far we got it to reach at this particular node? Okay, that is the first thing that we have to keep in mind. At any point in time, if it exceeds this k value, we will simply ignore that particular one. At any point in time, if status is offline, we will simply ignore that particular path. Okay, those two conditions we have to take care of. And while considering this particular path, we will keep on maintaining the minimum answer that we were getting it by following that particular path. If it is a valid, we reach at this last node, that is like we will keep maintaining that particular answer, whatever the answer that we got it. Okay, there is like this another path we have. So from this particular path also we get 6 as answer because that is a valid path. So we will keep on tracking that, and whenever we reach at the last node, whichever is the minimum answer that we are getting it by following that part, we have to make sure that previously whatever the value that we got at this particular last node, if it is actually greater than this new with this particular new path, if it is actually greater, so we will simply update the value. Okay, so by following this particular approach, we have to just make sure that when we reach at particular node, by following this particular path, when we reach at this particular node, 5 is the answer that we are getting it. By following this particular path, 3 is the answer that we are getting is minimum answer. So we will maintain another array where we will keep on tracking this whatever the answer that we are getting it to reach at any particular node. Okay, we may have different approaches, right? Like to reach at this particular two. Okay, so we have to make sure that we will keep track of what is the best answer so far that we got it to reach at this particular node two. Okay, from here 5 is the best answer that I got it. Okay, so anyway this particular part gives me best answer comparing with this particular path, because following this particular path to reach at this two node, I am getting 3 as a minimum answer, right? So at any point in time, minimum is out of all this particular node, minimum is the answer that I have to consider. So to reach at this particular node 2, I get already best answer, that is 5. When we consider this particular path, 3 is the answer that we are getting it. So when we go with this particular way, we may end up getting 3 as a minimum answer. Of course, we have again further 3 as minimum answer, but obviously, if I am getting from this particular best answer to reach at this particular node, I don't want to consider this particular path or this particular path. Okay, because for following this particular path, 4 is the answer that we are getting it to reach at this particular 2 node. Again, I don't want to pursue going with that 4 as a value. So this is the best answer that we are getting it. So we will maintain array or hash map, and we will keep on tracking what is the best answer so far that we got it as to reach at this particular node. So if from any other path, if I am getting different answer, so I'll simply ignore that particular path. So let us say that from here to here, to reach at this particular 6, I got 6 as a best answer, because comparing with this 10 6 minimum answer that so far I got to reach at this particular 6 was 6. Correct? Out of this minimum is something what we are considering, right? Total in minimum is something what we are considering. So 6 is something what we are getting it from this particular path. Now in a event when I start traversing from from here I got 3 is the minimum answer. Comparing with 5 and 3, 3 is the minimum. Previously 6 was the best answer that I got it. Obviously I don't want to consider this path. Okay, whatever the answer, even from here to here I got 5 as the best answer, so I don't want to follow this particular path. So this way we are just trying to optimize our code by not considering all the different solutions at any point in time. At a given node, if we got the best answer so far by exploring that one, we will just maintain that one. For that, we just have to maintain another array where we can keep on tracking like what is the best answer so far we got it at any point in time following from any particular other path. If we reach at that particular node and we got minimum answer as less than comparing with what was the previous answer, so we will not put it into the queue. Okay, so simple BFS approach or DFS approach we can use it, and we can solve this particular question with that approach. So time complexity in that case is like V, like total vertices that we have or nodes in total cross E, total edges that we have. Okay, that is the complexity, because we are trying to explore all the different nodes right over here. Okay, of course we are just optimizing slightly, but this is in the worst case, definitely this goes to all the way V cross E. Okay, that is the idea behind this. That is the brute force approach that I have explained right over here to you. So that basically works. I tried writing that code as well, and it worked for this particular question. But obviously, we have better algorithms available with us. Like as I already said, whenever minimum out of all the maximum or maximum out of all the minimum, this type of statements that we get it, we can try out with the help of this binary search, whether we can solve this question with the help of binary search or not. That is something that we have to give a thought process. Okay, let me clean these things, and we will discuss about the binary search logic, and I'll write down the code, and we are done with this one. Okay, it is quite easy. Just need to solve some of the graph related questions. Like we in total we have just 15 to 20 algorithms, and based on that only we have to solve different questions from the graph, right? So make sure to solve all the questions that are available in the graph, so that it will be really easy to solve any kind of this type of questions. Okay, so yes, let me just clean these things, and then we will start discussing about this binary search. And of course, this weight is also it is given. So whenever weight is given, so we will try to think about Dijitra's algorithm, whether we can apply that particular algorithm right over here or not. Okay, so binary plus Dijitra's basically gives us the best answer, and its complexity is also less compared with the previously V cross E that we thought of. Okay, let me clean these things. Okay, let us see how we can apply this binary search, and we can utilize the Dijitra's algorithm to solve this one. Okay, so but for binary search, I definitely require a range in which this data should be in a sorted order, like whatever the range that we are having. So here, the maximum answer that we can achieve from this particular one is 10, correct? That is the in worst case, like 10 is the answer that we can get it. Okay, so range can start from 0. Okay, the minimum answer that we can get is 0. okay, and it goes all the way to 10. Okay, that is the range. In this particular range only the answer basically lies. Okay, because this particular path, when we follow this particular path, correct, so here 6 is the best answer that we are getting, and that basically relies in this range only. Or from following this particular path, 3 is the answer that we are getting it, or from here. Okay, that is also relying in this particular range. Okay, so I guess this idea is pretty much clear, like why we are considering this range. So maximum among all these nodes is basically 10. 10 is the best answer that we can get it at any point in time. So this range could be from 0 to 10. Okay, that is the range for us. Okay, now what we will do is we will try to generate all the different answers, right? So whenever we solve any question with the help of binary search, what we do is basically we will try to get the mid of this range. Okay, so mid of this particular range is like 0 plus 10 divided by 2. Okay, 0 plus 10 divided by 2, that is 5. 5 is the midpoint that we are getting it. So what we will do is we will simply try to check whether this 5 is the best answer, and it is, I mean, it is giving the solution or not. Okay, with the help of 5, can we generate a solution? Okay, so what it try to simply say is like, when I consider this particular path, okay, it is not updating. From here, answer that I am getting is 8, but still this particular node is not a valid one. When we add these all the values, it exceeds this k value, but from here 8 is the answer that we are getting it. From this particular node, this is a valid path, and 6 is the answer that we are getting it. So our answer was 5. Our assumption was whether this 5 is the correct answer or not. And at any point in time, if any particular path basically gives greater than or equals to this value, that is 5, that is a valid one. Okay, whenever we reach at starting from 0, when we reach at this particular last node, and by following that particular path, if we are getting answer greater than or equals to this 5, because from this particular path 6 is the answer that we are getting it, which is actually greater than or equals to this 5. It is actually greater than this 5, right? So yes, this 5 could be an answer. 5 could be an answer. So lower than this particular 5, do I have to worry about any values that are available like 1, 2, 3? Because out of all this range, best answer is something what we have to figure out. The maximum answer that we are getting, that is something what we have to figure out. So following this particular path, we are getting 6 as an answer, which is actually greater than this 5. That means I don't have to worry about all the values that are lying in this area. So my focus would be, now I'll shift whatever the low, currently low was pointing at this one, high was pointing at this one, medium was right over here, midpoint. So my low, whatever the low that is there, it should start pointing mid plus 1. So low should be now 6, and the high is basically 10. So that is the range that we will be having. That means it is clear, right? So obviously out of different solutions, like we get it like from one following particular path, 3 is the answer that we get it. By following another path, like again 3 is the answer that we got, and 6 was the answer. These 3 different answers that we got, right? From here it is 3, from here, sorry, from here it is 6, from here it is 3, and from following this particular path, again 3 is the answer that we are getting it. Okay, so obviously 6 was actually greater than this 5. So I don't want to go back and check whether my answer basically relies in this area. All these values that are there, like 0, 1, 2, 3, those could be answer easily. 3 was there, that was an answer. But I don't want to worry about values that are less than this 5, right? I actually wanted to see the best answer, that is like the maximum answer that I can get it from this one. So obviously if any particular path giving me answer greater than or equals to this the assumption that we were having, obviously this low should start pointing mid plus 1. At any point in time, if the answer is basically whatever the assumption that we have done, 5 was our assumption. Okay, by following this part, 6 was the best answer that we are getting it. Let us suppose this path is also invalid path, like k value in this case is actually less than this, or 22 is something what we are getting. K value is 21. 21 is the k value that we have. So this path will definitely be an invalid path. Okay, so from here, whatever the answer that I was thinking, like 6 was, I'm getting it, I don't get it. But by following this particular path, I was getting 3. By following this particular path, I was getting 3. And our assumption was 5. Obviously, this 5 assumption that we have done, it is not giving the correct answer, right? Because the best answer that we are getting is 3. Okay, by following any part, best answer that we are getting is 3. So my range should, whatever the high basically was pointing right over here, it should start pointing to mid minus 1. Okay, that is the range. Now the answer basically relies in this range only, because 5 is not answer, then obviously whatever the answer that is lying in this range, okay, 6, 7, 8, 9, 10, anything, those are not a valid one, because 5 itself is not even supporting that. How it is possible that any other values apart from 5, like 6, 7 greater values that are there, those how it will support, right? So obviously high should start pointing to right over here, mid -1. So that's how the range basically squeezes. Okay, now in this particular example, whatever we have, this whatever the 5 that we got it made, 6 was basically supporting, because from here 6 was the best answer that we are getting it. So our assumption was 5, but we are basically looking at 6, the correct answer that we are looking at, right? So yes, obviously our range should now increase. So whatever the loop currently was pointing right over here, it should start pointing to mid -1, sorry, mid +1. So now the range got increased. Okay, range got increased. Now low is basically pointing to 6, and high is basically still pointing to 10. Okay, now when we try to get the midpoint right again, okay, now we will update the answer was basically 5 in current state, but obviously we can get the best answer, right? Like 5 is not even available in this particular range, we have availability of 6. Okay, and of course with the help of this particular algorithm we can easily reach out to this 6. Okay, so now the range got squeezed. Now low is basically pointing to the 6, high is basically still pointing to 10. Okay, and what how we are getting this answer is like we will use Dijkstra's algorithm that I'll explain you. But this particular way we are just trying to see with the help of this binary search whether we are getting the answer or not. Now the range got squeezed. So 6 to 10, the mid is basically 8. Okay, when we add this and divide by 2, the answer is basically 8. So mid is basically pointing to 8. Now we will check that whether 8 is the answer or not. 8 is the answer or not. That is the question for us. Okay. Now when we again start looking in this particular one, when we start following, sorry, when we start following this particular path, it is invalid. So this is not a valid one. When we start looking in this path, the answer is basically 8. This is valid, but when we see that here it is 6. 6 is the value that we are getting it, but the mid was basically 8. So definitely this path basically gives us 6 as an answer. We are looking for 8. So this is not a valid path for us. When we start looking in this part, 4 is the value that we have, and our goal was to look for 8. So this is not even it. At the start only it won't consider like we have to go in this particular path. Immediately, if at any point in time, whenever the weight is basically less than or equals less than this, whatever the assumption that we have, we will simply ignore that particular path. By following this path also, like 5 is the starting value that we are getting, and the answer was to get a 8. Okay, out of all these different paths, okay, the minimum value should be 8. Out of all these, what minimum value should be 8, or greater than that also it is fine, it is acceptable. But by following this path, 5 is what we are getting it, and the goal was to get 8, right? So this path is also not valid. So none of the path are valid for this answer 8. Okay, so if no answer we are getting it, like if at any point in time we are not getting answer related to this mid that we are assuming, so of course the high should start now pointing to mid -1. So now range got squeezed again. Okay, so range got squeezed. Low was basically pointing to 6, that was going to be there. Low is basically pointing to 6, and mid was 8. So high basically point to 7. So this is now the new range that we got it. New range that we got it, 6 to 7. Okay, where here the high is basically pointing. Okay. Okay, now again we will try to get the mid between these 6 and 7. So when we add them, 6 plus 7 is 13, divided by 2 is basically 6. So mid is basically 6. Okay, so we will try to see whether 6 is the answer that we can get it. Okay, so we will start following this again same. We will try to go this particular loop. So here 10 is there, so it is valid, but when we come here, 6 is again still mid is actually greater than or equals to this valid. So this particular path we are giving, it is giving us the value as a 6, which is less than or equals to this 6. Okay, so yes, it basically returns true at any point in time when we reach to the last node. Any particular path giving us the answer that we are trying to assume greater than or equals to that particular answer. Okay, whatever the mid value that we are having, if it is actually greater than or equals to this mid, whatever the answer that we are getting it, so yes, it is a valid one. Okay, so answer is by following this particular path, 5 is basically actually less than this mid. So this path itself is not a valid path. Okay, this whatever the path that we are considering, because going down from here, of course 5 is value that we are getting it, and our goal is to get 6 as the best answer. Okay, by following this path, 5 is what we are getting it, which is actually less than this 6, right? So how it come this particular path will give us the best answer. Okay, here again it is giving 3. So it doesn't make sense to go and follow this particular path at any point in time. If these values are basically greater than or equals to this mid value, then only we will consider going into the path, because that way only we'll get to know that at the end this particular path may give us 6 or greater than or equals to 6. Okay, by following this particular path, 3 is what we are getting it. Here itself it is saying that I am not having this capacity to give you 6 as an answer, right? Right, 6 is the answer that we are looking at, and this particular path is giving 4 start of it itself. So by following this part, minimum is something about like 5 3 6. 3 is the minimum that we are getting it. So how come this particular path will be a valid one? So here itself we will stop exploring this particular path. From here also same, like 4 is the minimum that we are getting and the answer that we are looking for is 6. Okay, by following this path we will never get 6 as an answer. Okay, by following this particular path also we will never going to get 6 answers. So there itself immediately we will stop by exploring these paths. Okay, that is the uh, best thing that we can get it by following this particular one. Okay, so I hope you get this idea like what we are trying to do now. 6 is valid one for this particular path, so the answer will get updated. Since it is valid one, so this answer will get updated to 6. Okay, and that is the answer that we are having. Again, this 6 is valid one, so low is currently pointing here, so low should be point to mid plus 1. So low is basically pointing to the same as high. Okay, so it doesn't matter until and unless high and low are basically equal, it is fine. The moment high basically goes here or low goes here, okay, if they crosses each other, we will break out of this whatever the binary search logic that we are having. Okay, so now both lows and highs are pointing to 7. So mid is also 7, low is basically 7. Answer already got updated to 6 now. Okay, and then high is basically 7 and mid is basically 7. These are all the values that we have. Okay, now we will check for 7 whether 7 is the possible answer or not. Okay, this particular path is actually invalid one because its sum is basically going out of this key value, so that is not a valid one. This particular path, when we try to explore, 6 is value that we are getting it, and our goal is to look for 7. So this is not a valid one. Here, from here 5 is what we are getting it. This is not a valid one. When we start exploring, this is also not valid one. So no values we are getting it which is actually matches to the 7 or greater than this 7. Okay, by following any particular path we are not getting the answer greater than or equal to this 7. Okay, so that's it. Like at any point in time, if it is not matching, this high should point into mid minus 1. So high is now, low is basically pointing and high is pointing to same one. Okay, both are pointing. Now the moment high points to high basically less than this low or low greater than this high, we are done. We will simply break from this particular loop. Okay, I guess this is clear what we have done so far with the help of binary search. Now the idea is like we just have to put whenever the mid value that we are getting it, we just have to check whether the this particular answer is satisfying or not, and for that we will use simple Dijkstra's algorithm. Okay, you should have idea about this Dijkstra's algorithm. Okay, I am not focusing truly on this particular algorithm. I'll make sure to create another video for this Dijkstra algorithm. We have different ways to solve this particular one. So it basically helps us to get the minimum path sum by following any particular route. Okay. So for that one, simply what we do is basically we will maintain an array which keeps track of what is the minimum answer so far we got it by following any particular path. So from 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so far what is the minimum total path sum that we are getting it, that is something what we will keep on tracking in this particular one. Okay, that is the goal, whole idea in this one. Now next is like initially 0 for 0 it is like 0, and all these values are basically filled with the max value. Okay, whatever the integer dot max or long value, if we are having long whatever the long max value that we are getting, that is something what will keep on filling into this particular array. That is the first step to solve any question with the help of Dijkstra's. Okay, now once we are done, we can use priority queue or we can use normal queues. We have a number of options. For here I'll use priority queue, PQ, to put the data, and in the priority queue whatever the weight that we got it, the minimum weight, that will be available at the top in the priority queue. Okay, that is something what I'll keep on tracking. Okay, now the goal is we have to start from 0 and we have to reach to the last node. Okay, that is the goal. We will simply initially we will fill it with 0, 0, 0, 0. That is something what we have. This 0 is basically pointing to node, the node at which we are at. So initially we are starting with 0. So 0 is something what we have. Next one is like the total cost. Total cost is something what we are considering. And I don't think we have to track here the minimum value. The minimum value is basically for us is like whatever the mid value that we are considering, that is the value it should satisfy at any point in time. Okay, that is the whole idea. So we will simply put here in this priority node and the total cost so far that we got it. Okay, at any point in time, this total cost, whenever we start exploring any particular node, if it exceeds this k value, we will simply break from that one. That means like we don't want to put that next node into the queue. Okay, that is the whole idea. So initially 0, 0 is something what we have. Okay, from 0 we have 3 different nodes. Okay, so mid was initially like we have range from 0 to 10. 0 to 10, so mid is basically 5. That was the mid, we got it right from 0 to 10. So 5 is whether 5 is basically answer or not, that is something what we were looking at, right? So simple idea is like whatever the data that is available in the priority queue, that is something what we will pull, and we will check what are the adjacent nodes for this particular 0. So these are like these 3 adjacent nodes that we have. The first thing that we will check is whether this whatever the edge weight that we have, if it is actually greater than this mid value or not, greater than or equals to this mid value or not. So the mid value was 5, it was 5, mid value was 5, correct? That was the value that we got it. So this 10 is basically greater than that or equals to that, and we will check that whether this is one is basically online or offline from this one. So both are satisfying. This value is basically this greater than or equals to this mid, and this one is online. So simply we will put this into the priority queue. Now the queue will be having this one, and whatever the previous total cost that we have, we will simply add this one. Okay, that's how we are. So that's how we will get the total cost, right? So whatever the previous cost so far that we got it by exploring that node plus previous cost, this current node cost, this age. So here initially 1 and 10 is something what we will put it, because 10 plus 0 is basically 10. Previously 0 was something what, because we started from 0, so we don't have any cost, right, at that point. That is something what I have put it into the priority queue, and I'll update right over here as well. So 10 is something what I got it right over here. Okay, 10 is something what I have got here. Now next is like for 0, next node is addition node is like here, that is 2. So the mid is basically 5, this is 5 is basically satisfiable, so we will put it into the priority queue. So PQ looks like this, 2 comma. So previously for from 0 to 2, the total cost is like it was 0, right? Here it was total cost was 0 previously. In the priority queue, total cost was 0 for 0. So 0 plus this particular edge cost, it is 5. So 2 comma 5 is something what I wanted to put. Here we are just maintaining the current node and the total cost that we are getting it. Okay, because 2 is obviously online from the status array, online status array. Yes, we can easily put it into the priority queue. Okay. So we are done with this particular node. Like from 0 to 1, there was one path. That is something what we have explored. From 0 to 2, there is some path. That is something what both the nodes are basically valid ones. So we put it into the priority queue. Third one is like this edges between from 0 to 3, there is an edge, and its weight is basically 4. Now here we simply check that whether this weight is basically matching with the answer that we are checking, right? So definitely going ahead from this particular path, here itself 4 is something what we are getting minimum value. So at any point now, if all these values are maximum, let us suppose 10, 20, 20, something like that, but initially itself 4 is something what we are getting, right? So minimum is something what we will consider by following any path. That is the first thing that we have. So obviously this particular path doesn't make any sense, so we don't want to put it into the priority queue easily, right? That is the whole point right over here. So at any point in time, whatever the answer that we are assuming it, if it is not matching with what the age weight that is being given, if it is less this whatever the age that is given, if it is less than this answer that we are trying to think of, definitely this is not best way to go, and we don't want to proceed with that particular uh, in that particular direction we don't want to go. Okay, so I don't want to put it. Now we explored all the nodes that are available for this 0, so this was taken away from this priority queue. Now the priority queue has these nodes. Okay, this is the at the top, this is at the second. So based on the, I mean, we are sorting this data, so this will be available at the top based on the minimum weight that we have, but it doesn't make sense for this particular question. Let us sort this one. So it is like 2 and 5 is actually at the, available at the top. 2 and 5 is available at the top, total cost that we have. So we will pull out this from this queue. So this will be not available. Now we will check for this particular 2, for this particular 2, which are all the adjacent nodes that we have. This is the first node that we have as an adjacent, correct? Do we have any nodes that are going in outside of this particular 2? Like is there any out degree that is available? No, right? Only one node is there that is having age from 0 to 2 to 6. Yes, that is something what we will consider. Here the weight is basically 3. Again, we will simply check what is the mid value. 5 is the answer that we are looking at, and 3 is something what we are getting it. So by following this particular path, the answer we may get it as a 3. So simply this is not a valid path, so I don't want to proceed with this one. Okay, do we have any other nodes that are going outside of this 2? No, right? Only one age is something what we have, that is something what we have processed. So that is something what I'll take out from this one, and we don't have this particular node as a valid one, so we are not putting it into the priority queue. Next is like from 0 to 1, we already put it into the priority queue. Okay, so that is something we will try to take out, and for this one we have these two edges that are going outside. Okay, the which are having these two adjacent nodes. Okay, 1 to 7, the first is like 1 to 7. Total cost so far was 10. Here it is 8, so 8 plus 10 is total 18. Okay, in total it is 18. So by following this path so far to reach at this 7, 18 is something what we are getting it, and here it is 26, so it is still valid. So yes, we can put it into the priority queue, because this 8 that we have is actually valid one. Mid is basically 5, 5 is something what we are looking at, and here 8 is something what we are getting it, right? So yes, this is actually a valid path. So yes, we will simply put it into the priority queue. So since it is taken out, so it is not available, but whatever the adjacent nodes that are there, we will keep on processing for them, right? So 8 is now this total cost is basically whatever the previous cost but new cost, that is something what available right over here, and the node is basically 7. Okay, so we reach from here to here, from 1 to 7. 7 is something what I have put it right over here, and 18 is the total cost. So far we got it. Okay, so simply next is like from this one, here is another node that is going outside this particular edge is going, right? So its cost is 6 and mid is basically 5. So yes, this is a valid path, this is a valid node, right? This whatever this path particular we are considering, and total 6 plus 10 is 16. 16 is what we are getting it, and here the goal is like 26. It should be less than this 26. So yes, this is a valid one. We can consider it, and all these nodes are basically online based on this online offline whatever this status that we have. Yes, this is a valid path, so we can consider putting it 6 plus whatever the previously total cost was 10 to reach from 0 to 1. It was 10, right? And now this new one is like 6. 10 plus 6 is basically 16. Okay, that is something what we will put it in the priority queue. Okay, so this will be available at the top, 6 and 16 in the priority queue, because based on the weight we are sorting it. So this is what it looks like: 6, 16 basically available at the top, 7, 18 available at the bottom. Now from 6, okay, whatever the top data is available, we are simply taken out from this priority queue. Okay, so we are just simply pulling this out from the priority queue. It is basically queue, right, ultimately, but since priority queue is we are using it based on the whatever the data we have sorted, either ascending or descending, it will be available at top. So this is something what we are taking out from this priority queue. 6, 16. From 6, do we have any nodes that are going away? Yes, this is the node, right? And we are reaching to the last node end. Okay, so we will keep on updating these values. Okay, so 6 for this 6, now this new value was basically 16. Okay, 16 is something what we got it new value right over here. Okay, that is something what I'm keep on tracking it. So in Dijkstra we basically maintain a maximum whatever the best answer that we are getting it. Okay, so far, and instead of this total wage cost age weight, what I'll do is I'll maintain the minimum answer so far that I got it. Okay, and that should be maximum also. Okay, so what I'll do is instead of here 16, instead of maintaining the weight, what I'll do is I'll maintain the minimum answer so far that we got it. 6 is the minimum answer that we are getting it. That is something what I want to update in this particular one. Okay, so yes, that is what we are doing it, or even the weight is something what we can keep on tracking. Ultimately, this last node is something what our goal is to reach into this last node. So this last value, whatever we have, it shouldn't be long dot max value. It should be getting updated with any particular value. Okay, whatever the sum that we got it, either with that or minimum value that we are tracing out. That is something what we have to keep on updating into this particular array. Now 6 and 16 we pulled out. We have only one edge, that is like this one going from the 6. So we will simply check that. So far 16 was the answer we got. 6 and 16, 22. 22 is actually less than this 26, and even this values are basically online. So yes, we can consider this. So this is the last node that we reached out, 8, and basically it is the answer that we got was basically 22. The moment we reach to the last node, we are done. Like this particular whatever the mid answer that we were considering, right, it is a valid one, because by following this mid value we got a particular path. The moment we reach to the last node, we are done. We will simply break out of from this particular one. Okay, let us suppose now the mid was basically 5, so this got satisfied. By following this particular, I was taking out this from this particular priority queue, and this 10 is basically when we add it, it goes beyond this k, so this is not a valid also. And the mid was basically 7, like that. Mid is basically equals to 7. So this particular path is also not a valid path in that particular case, because 7 is something what we are looking at, and here itself 6 is something we got it. By following this particular path, 7 is something what we were looking at, and 6 is something what I got it. Okay, so obviously this is not a valid one, so none of the answers were matching to this mid value, so we will break out from this one. Okay, that I hope we will keep on doing the same operations. Okay, so this Dijkstra's algorithm we will keep on performing for all the different mid values that we are getting it, and this way we can solve this question. Okay, I hope you get the idea. Let me write down the code as well, because it is taking a lot of time. It took around 40 minutes, so writing the algorithm again it takes 10 more minutes. Okay, I'm not writing down the code. It will take further long time. I'll simply explain you what it is, what I have done, and how you can write the code. So basically, the first thing is like it is already said that this 0 and 1 are online. Okay, node 0 and node n minus 1, last node and first node are online. So our goal is to just check whether the intermediate nodes are offline or not. Okay. So as I said, like we are using the binary search, so we require high and low. So initially low is basically 0. High is something what we have to figure out. That we will do it by while creating the adjacency list. Okay. So n is something what I have get it from this size. Then this particular condition doesn't make any sense at any point in time. Okay, so I was not aware yesterday whether I have to do it or not, so that's why I have done it. I didn't read it carefully, so that is something what we can simply remove it. Next is like this is the adjacency list that I'm creating out. Okay, so array list of array list. So in basically how it basically holds the data is like for 0 I do have path between, like let us suppose there is path from 1 to 5. So first is like 1 and 5 it will hold. 2 I have any other path, like from 0 2 to 3 is another one. So 2 and 3, that is how I am basically storing the data. Okay, so for 0 there is a list which basically holds all the node and their weights. Okay, so initially we have this list of for all the 0 to n. So I have to create the objects. Okay, in each list I am holding an array of data. Okay, so this is like in form of array. Inside this list I do have data in form of array. So the zeroth location will be the node and the first location is like the weight, the cost that is there from 0 to 1. Okay, from 0 to 2 the cost is basically 3. That's how I'm storing the data. So yes, this edge graph that we have given, so I just created that. So the whatever the 0th location that we have, edge of 0, I get it like I have created this list, right? So I get that object. In that one I am adding this new int of h0 sorry, h1 and h2. That is like for 0 I pulled out the list. Inside that list I am storing this 1 and 5. Okay, that is how our first object has been created. Next is like again when we get this edge while following this for loop, so again I get the list of this for 0 to 1. I'm adding another data that is like in a form of integer array inside that list. So that data is like 2 to 3. That is something what I have put it inside there. And I am keep on tracking this high value, which is the highest value that I'm getting it from this array. Okay, from this all this array. So the highest value for this particular one is 10. 10 is something what I have keep on maintaining, like what is the highest cost that we have. Okay, the high value is also done. Low value is also already, it starts with 0. Now we will simply apply the binary search logic. So low until and unless this low is basically less than or equals to this high, we will keep on trying to generate the answers. Okay, this is the best answer that we can get. That is something what we will keep on looking at. So answer is basically -1 initially. So at any point in time if we do not get any valid path, we have to return -1. So that's why I have created this answer as -1. Okay, low is something what we will try to generate, as I already said. So we will get the low, that is the mid value. Sorry, this mid is something what we will generate, and that is something what we will get it, low plus high. Now we have to just check that whether this whatever the mid value that we are getting it, whether it is a valid or not. Okay, so whatever the answer that we are assuming, this whatever the mid value that we are getting, that is the answer that we are assuming it, and we will check that whether this mid is the answer or not. Okay, for that I have created this is this solution function, which basically returns true if this mid is basically a possible answer or not. Okay, so mid is something I have passed right over here. The list is something like the array list, the adjacency list that we have created, that is something I have put the online status, offline status, k value. Okay, and the total number of nodes that we have. Okay, if at any point in time that whatever the mid value that we are considering, if it is the solution, we will simply update it with the answer, and low should starts pointing mid plus 1. At any point in time, whatever the mid value that we are considering, if it is not an answer, the high should point to mid -1, because if that value mid value if itself does not satisfy this one, obviously higher value is never going to satisfy us. So we have to shift our high to mid -1. Okay, if it is satisfying, we will try to check whether any higher possible values that we can get it, because maximum something what we have to achieve, right? So that's how we are doing it. So now is this possible solution, we pass the mid, whether we are just checking that whether this cost, whatever the cost that we have, if it is satisfying overall to this code or not. Okay, so cost is something what we got it right over here. Now, for the Dijkstras, we will simply have an array which maintains the cost at each location. So that is something I have created. In this code, we can have this cost arrays like in different ways. I can even track of least value that I got it so far for each node, or we can carry total cost that we got it so far, and that way it will be helpful whether we will check that whether whatever the cost that we got it, whether it is actually greater than this k value or not. Okay, so there are multiple ways we can write out. So here in this one I am just keep on tracking the maximum cost so far that I have got it. So the end goal is like whether with this particular flow, whatever the path that we are considering, whether we are able to reach to the last node or not. The moment we reach to the last node by following any particular path, this particular cost is actually a solution for us. So we will simply return true from here. Okay, that is the end goal. Okay, now I have created this array. I'm filling this all this value with the long max value. We are considering long value because when we sum these elements, we may go out of bound. The range may be not sufficient, so I consider it as a long. Now the next is like we will create a priority queue. Inside priority queue, the first will be holding a node, and next is like the total weight so far, the total cost that we got it so far, that is something what I am putting it at the second index of this long. Okay, the first index basically denotes the node at which we are at currently and the total cost so far that we got it. These two values are something what I am maintaining it inside this priority queue, and it is basically sorted based on the total cost. Okay, inside priority queue, the first is like 0 0 is something what we have to put because from 0 only we are starting it. So we will keep on running this while loop until and unless the priority queue is empty. The first is like we will pull out from this priority the current data. So it is like 0 0 is something what it will take out. Node is basically at 0th location. The cost is basically at the first location. So far the cost that we got it. So at any point in time, this current cost that we got it, if it is actually greater than this cost area of node, whatever the cost area. So minimum value is something what I am tracking out. So simply the whatever the Dijkstra algorithm that we have, that is something what I have applied right over here. So if it is that, if that is the case, then I'm simply what I'm doing is like I'll continue because I don't want to get highest value so far while reaching at particular node. If I am getting lowest sum so far, then I don't want to consider this the new one and wanted to recalculate re-go further. Okay, so yes, that is for that this condition basically realized right over here. Next is like basically the moment when we reach this whatever the node that we have, if it able to we able to reach it to the last node, that is like that is the goal, right? So the moment we reach to the last node, that means like we are done. So I am simply returning true. So this is like early exist that I am doing. I don't want to recheck like from any other path whether I am able to reach to this last node or not. The goal is not that. The goal is whether this cost that we have, if it is satisfying, okay, this particular cost, that whatever the cost that I am considering, if it able to satisfy me and I am able to reach to the last node, that's it. Like any particular path take me to the last node, I am done. I don't want to further recompute whether any other way I am able to reaching to this particular node or not. Okay, so for that like we can use this particular condition. So this basically takes us out earlier. Okay, now once that is done, we are checking like all the adjacent nodes. If it is not last node, we have to check that whatever the adjacent nodes that are there, we will keep on pulling them up and we will check their weights. If their weight is basically less than this cost, okay, whatever the cost, that means that path is not a valid path because ultimately this weight, whatever the weight that is there, that is like minimum weight is something what we will consider ultimately for that particular path, right? If that particular path weight is basically whatever the path that weight that we are getting, if it is actually less than this cost, definitely it is not a best solution. So we will break there itself. We don't want to put it into priority queue and we can further we want to compute it. So that is this first condition, and we will check that whether that particular whatever the RSN node that we are looking at, if it is offline, in that case also we will simply continue. Okay, these two conditions basically make sure that we are not processing any invalid path. Okay, and its status is also it is a valid one. Next is like the cost, total cost so far we are getting it. Previously the current cost was this one for the current node. Now the for this addition node, the cost is basically this weight. Okay, whatever the weight. So when we add this new cost, that is what we are getting it. Two conditions we are checking it. If this new cost is basically less than this cost area of y, typically this statement says that we are using the Dijkstra's algorithm. So in Dijkstra's, we will keep on maintaining the minimum cost so far to reach that particular node. So that is this condition basically says that. And next is like this new cost should be less than or equals to this k value. Okay, if it is actually greater than this k value, I don't want to put it in the priority queue. Okay, three conditions we are just applying. If it is offline, online, if it is not online, okay, I don't want to put it into the priority queue. If the new cost so far the cost that we are getting, if it is actually greater than this k value, I don't want to put it again into the priority queue. Okay, and last is like this, whatever the weight that we are having at that particular node between the nodes, okay, it should be greater than this cost value or equals to this cost value. If it is less than this cost value, simply I don't want to put it again into the priority queue. These three things helps me to early exist from this particular one. Okay, at any point in time a particular path is there, so that with the help of that I am able to reach to the last node. That is something what it basically says. Okay, so instead of putting right over here, we can put it inside this one only. Like if at any point in time, if node is basically last node, because I don't want to this in the priority queue data is basically in a sorted order, so maybe we proceed with further extra nodes, so I don't want to do that operation as well. So I simply check that this whatever the adjacent node that we are at, adj, if it is actually equals to n minus 1, okay, I'll simply return true from there. Okay, we can put it at this location at well. Okay, because since all the conditions are satisfying and we were able to reach to the last node, so we are done. If it is not a last node, we have to consider updating the cost array with this minimum value, and priority queue, in the priority queue we will put that addition node and the new cost that we are getting it. Okay, so if at any point in time if we are not able to reach to the last node, we will simply return false. So that means like there is no possible way to, with the help of this particular cost, we can get the answer. Okay, whatever the minimum cost that we are considering from all the different path, this cost is something what we are considering, right? It is not a possible solution, so definitely high should point to mid minus 1, or else low should point to the mid plus 1. That's it, like it's pretty much straightforward. This particular while loop, it basically takes log of maximum value that we are getting, like this high value is something what we are considering. Okay, log of this high value. Okay, that is the first thing. Next is like multiplied by this particular solution is basically we are considering the Dijkstra's algorithm with further optimization in that particular one. So obviously Dijkstra's code basically takes whatever the edges that we have. Let us suppose E are the edges, V are the vertices, log V, that is the complexity, we get it. So it is basically better than what we thought of with the first approach, that is like E cross V. Okay, so it is obviously better log of high cross E plus V log V. Okay, so definitely this is the best solution that we can get it, and further we keep on optimizing the code. So yes, this approach is best. Let me try to run this and see if it is working fine or not, and I'll put this into the description as well. Okay, line number 11 is having an issue, so of course it should be. Let us try to see if it is working fine or not. Yeah, it is getting accepted. Let me submit this code and see if it is working fine, so that I can simply put it into the comments and other can use it. So it is working fine, and yes, I guess this is fine. So space complexity is obviously I mean when we notice here, we are again creating the artisan list, so it is like V plus E. So that is basically the space. We are not bothering a lot about this space, okay, in this particular one. So I hope you get the idea what I have tried saying right over here. So if so, please make sure to like this particular video. Thank you for watching this one. Bye bye.